Alright, so here's the first lesson for trig. It's my second attempt on it, so let's hope this one goes a little better. So trigonometry is really the study of right triangles. We learned that a squared plus b squared equals c squared, and we did that with the Pythagorean theorem. When a or b increase, then c increases in a predictable but hard to calculate way. What do I mean by that? I mean, let's say I was increasing a but not b. Let's say that b stays the same. Let's see if we can find a pattern. So b squared is always going to be 16, so let's just write that. B squared is 16, and then a squared here is going to be 9, a squared here is going to be 16, and a squared here is going to be 25. So I'm looking at these triangles, and I'm saying, okay, a squared plus b squared equals c squared, so this plus this has to be equal to c squared. So c squared equals 25 here, because 9 plus 16 is 25. And then here, c squared equals 32. And here, c squared equals 41. So, let's see if we can see the pattern. This one, you add 7 to get from 25 to 32. Not bad. Here, you add 9 to get from 32 to 41. Now, that may not seem like a pattern to you, but let's do one more. Maybe you'll see it then. So let me write one more triangle in, and then I'll put in 6 and 4. So that's 16. And then this is going to be 36. And 36 plus 16 is 52. C squared equals 52. If you see the pattern, fantastic. But it's okay if you don't. Here, the addition is plus 11. And from here to here, this is the real pattern is right here. It's plus 2, and from 7 to 9, I mean, and from 9 to 11, the difference is plus 2. That's what's really happening when I increase this number by 1. The number that's increasing in between the c's, the c squareds, is increasing by 2. In fact, this is kind of like calculus. This is actually just a little glimpse into it and saying, oh, this is how this triangle is changing depending on what a squared we pick. So, and there's a function we can write to describe this change in c squared. It's really a squared plus 16 equals c squared. Why? Because I'm changing a squared depending on an a. I'll pick a different a, and it will give me a different c squared. But 16 is constant, so I don't have to worry about the 16. I'll just write plus 16. So I'll write a squared plus 16 equals c squared. That's my function, where a is my independent variable and c is my dependent variable. Now, I know some of you are going to say, but this is a relation, Mr. Fernandez, and I'll be like, well, how'd you know that? No, it's a relation, but in a way it is a function. If we don't worry about the c squared, it is a function. All right, so, but we have a problem. What if a and b are changing? This was nice and fuzzy and nice and easy when all we were changing was a. But if we're changing b as well, we have a problem. We can't easily find the pattern like that. But we can use our calculator. So, picking any specific value for a, b, and c forces one triangle into existence. It's just one and only one triangle. And that's because of side-side-side congruence. When we were doing that earlier on in the year, I showed you that was because we can divide any triangle that you draw into right triangles. And so when you pick 3 sides, there's a specific right triangle that will correspond to those 3 sides, maybe x, y, and z. So there's only one triangle that's going to be made because there's only 2 right triangles that are going to make up that one triangle. And then the same thing here. There's only 2. If I said maybe these are congruent, I can compare with side, 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 because automatically when I pick specific values for x, y, and z, it's going to give me a specific triangle because I can divide it up in 2 of the same right triangles. All right? Now, the thing is, because of this fancy thing, we can calculate angles based on sides and sides based on angles, and I'll show you how to do that next.